most expensive buildings human beings have ever constructed don't make cars, they don't make airplanes, and they don't make computer chips. They make sentences. Right now, across the United States and around the world, companies are pouring more concrete and pulling more electrical cable than at any point since the interstate highway era. Also, that when you type a question into a chat box, an answer comes back a couple of seconds later. In this video, I want to open up one of these buildings and walk you through it layer by layer: the electricity, the cooling, the chips, the wiring, and the economics. Because once you understand what's physically inside an AI data center, you'll understand where hundreds of billions of dollars a year are actually going and who's collecting it. Welcome to Level Up IT, the channel where we break down the technology shaping your career and your money. Let's get into it. Let's start with the question everyone should ask first. The internet has been around for decades. Search engines have answered trillions of queries without anyone needing to build power plants next to server farms. So what changed? Here's the way I think about it. A search engine works like a warehouse with very good shelving. All the work of stocking the shelves happened ahead of time, crawling the web, sorting it, indexing it. When your query arrives, the system just walks to the right shelf and hands you what's already there. That lookup is astonishingly cheap, fractions of a cent over and over, billions of times a day. A large language model doesn't have shelves. Nothing is pre-stocked. Every single answer is assembled on the spot, piece by piece, even if a million other people asked the exact same thing an hour ago. Estimates vary, but a single AI chat response can demand somewhere between 10 and 100 times the computation of a classic web search. Multiply that by hundreds of millions of users, and you get the entire story of the current build out in one sentence. We switched from looking answers up to manufacturing them on demand, and manufacturing needs factories. So let's tour the factory. I'm going to walk you through it in 5 layers. From the outside in: power, cooling, compute, memory, and networking. And finally, the software and the money. At each layer, I'll tell you which companies live there. Layer 1, power. Before a single chip does anything, you need electricity, and not household amounts. A large AI campus can draw as much power as a mid-sized city, measured not in megawatts, but increasingly in gigawatts. That's nuclear reactor territory. This is why you keep seeing headlines that sound bizarre until you understand the context. Tech companies signing deals to restart mothballed nuclear plants, ordering fleets of natural gas turbines, and buying land based not on internet connectivity but on proximity to substations. The bottleneck here isn't generation, it's connection. In many regions, the queue to hook a new large facility into the grid stretches years. Transformers, the giant units that step voltage up and down, have multi-year order backlogs. So the companies that make electrical infrastructure, switchgear, transformers, backup generators, uninterruptible power supplies have quietly become AI companies without writing a line of code. If you've wondered why sleepy industrial names in the power equipment business have seen their order books explode, this is why. Electricity is the raw material of this entire industry, and the pipes that carry it are sold out. Layer 2, cooling. Here's a rule you can't negotiate with. Every watt of electricity that goes into a chip comes back out as heat. All of it. A modern AI server rack can put out heat comparable to dozens of household ovens running full blast in a space the size of a refrigerator. Blow air over that, and you simply can't remove heat fast enough anymore. So the industry is in the middle of a forced migration from air cooling to liquid cooling. Cold plates bolted directly onto the chips with coolant loops running through the racks out to heat exchangers and cooling towers. Water becomes a site selection issue, plumbing becomes a competitive advantage. And the companies that design and build this thermal equipment, along with the specialized contractors who can actually install it at scale, occupy a layer of the stack most investors never think about. No cooling, no computing. Is that direct? Layer 3, compute. Now we're at the heart of the building, the chips. The workhorse of AI is the GPU, a processor originally designed to draw video game graphics, which turned out to be almost perfectly shaped for the math AI models run on. And that math at the bottom is shockingly simple. Enormous grids of numbers being multiplied and added together, trillions upon trillions of times per second. What a GPU offers isn't cleverness, it's parallelism. Tens of thousands of small calculators working simultaneously. One company, NVIDIA, dominates this layer and is worth being precise about why. It's not only that their chips are fast, it's that over nearly 2 decades, they built the software ecosystem, the programming tools, the libraries, the accumulated habits of an entire generation of AI engineers around their hardware. Competitors can match a chip. Matching 15 years of software gravity is much harder. That's the moat, and is why NVIDIA collects a toll on nearly every AI factory built anywhere on Earth. The chips themselves are manufactured almost entirely by one company in Taiwan, TSMC, using packaging techniques so advanced that packaging capacity, literally the step where chips get assembled together, has repeatedly been the bottleneck for the whole industry. And these machines are expensive in a way that's hard to internalize. A single fully loaded AI server can cost as much as a suburban house. A single building holds tens of thousands of them. Layer 4, memory and networking. Here's the part of the story that surprises people. The hardest problem in AI hardware right now isn't doing the math, it's feeding the math. A GPU is like a world-class chef who can chop faster than anyone alive, useless if ingredients don't arrive at the cutting board fast enough. Feeding it requires a special kind of memory called high bandwidth memory, stacked in layers, physically fused next to the processor. Only 3 companies on the planet make it in volume: SK Hynix, Samsung, and Micron, and it has been sold out essentially continuously since the AI boom began. When you hear that memory prices are surging, you're hearing the sound of that scarcity. Then the chips have to talk to each other. Modern AI models are far too large to fit on any single chip, so a model gets spread across hundreds or thousands of GPUs that must exchange results constantly at speeds where a few millionths of a second of delay multiplies into real money. This is the world of high-speed networking, specialized switches, network chips from companies like Broadcom, and staggering quantities of fiber optics and optical transceivers, the tiny devices that convert electrical signals into laser light and back. A single AI building can contain more fiber optic connections than some national telecom networks. Every one of those connections is a product someone sells. Layer 5, software and the money. Sitting on top of all this physical machinery are the models themselves and a pricing system worth understanding because it's the revenue engine of the entire industry. AI models don't process words, they process tokens, chunks of text roughly 3/4 of a word long. And tokens are literally the product. The model companies price their services per million tokens, the way a utility prices kilowatt hours. Every layer I've described, the power plants, the cooling loops, the GPUs, the memory, the fiber, exists to make tokens cheaper and faster to produce. When someone asks whether the AI build out makes financial sense, they are really asking one question: will the world buy enough tokens at high enough prices to pay for all of this concrete and silicon. And that brings us to the honest part of this video. The spending is real and it is historic. The 4 biggest cloud companies alone are deploying capital at a pace comparable to entire national infrastructure programs, and Wall Street projections for the coming years run into the trillions. But scale is not the same thing as certainty, and there are 3 cracks worth watching. First, depreciation. A highway lasts 50 years. A GPU is economically cutting edge for maybe 3 to 5 because next year's chip does the same work for less power and less money. This is infrastructure that melts. The revenue has to show up fast or the accounting gets ugly. Second, utilization. A factory only makes money when it's running. If model efficiency keeps improving, and it is rapidly, the same demand can be served with less hardware. Great for the world, complicated for anyone who bought hardware, so easy, assuming scarcity forever. Third, circularity. Some of the demand propping up this ecosystem comes from companies funded by the same players selling them the infrastructure. Chip makers investing in AI labs that buy their chips, clouds investing in startups that rent their servers. None of it is necessarily improper, but it makes the true organic level of end demand genuinely hard to measure from the outside. So here's how I'd leave it. The next time an AI answers you in 2 seconds, you'll know what those 2 seconds contain: a power plant's output, a river of coolant, a warehouse of house-priced machines, memory 3 companies can make, lasers threading glass fiber, and a token counter quietly ringing up the bill. The factories are real. The machinery is real. The open question, the trillion-dollar question, is whether the sentences they manufacture are worth what the factories cost. Watch the token demand, watch the utilization, and watch the depreciation schedules. That's where this story will be decided. If this helped you see the AI boom a little more clearly, subscribe to Level Up IT. There's a lot more where this came from. See you in the next one.